Refraction, lesson number 6. Now that we've worked the math through here, we can actually see the critical angle, the most it could possibly be, is 24.4 degrees. Any more than that, and refraction will not occur. So we go back to our chart. The highest number that we can go to is 24.4 degrees, and then still have it work. Well, this begs the question, in reality, what happens after we've exceeded the 24.4 degrees? And the answer to that question is this. Once the light rays reach a certain critical angle, and let me redraw, they can no longer refract. So if we look at a light ray coming in, and let's make the angle 40 degrees, what the heck? All right, so it comes in as measured from the normal at 40 degrees. And there it is. Remember now we're still in diamond, which has a very high index of refraction. Well, it can't refract, so what's it going to do? And the answer is it's going to reflect. So the glass becomes as a mirror, and then it follows the laws of reflection. So if it came in at 40 degrees, it's going to exit at 40 degrees. Now, if we take a look at various situations, let's say we have some type of tubing. This is plastic tubing. Doctors use this, for example. In the old days, they used to slice you open and your guts would be pouring out. Now we can take a little slice and then place tubes. So let's say, for example, they want to check down in your stomach. They just kind of thread the tube down there. All right, and these tubes are based upon the laws of refraction and reflection. If we take a look here, let's draw that tube and see what's going on. So as we look at the tube itself, it's basically just a piece of plastic that's flexible. Now, if I send in a light beam into this tube, like so, if the angle is shallow enough and it's exceeding the angle, the critical angle, the tube becomes as a mirror. So if the angle is too shallow, too steep actually, and it exceeds the critical angle, it's just going to start ricocheting back and forth inside the tube like so. So if we look here, the light gets trapped inside the tube. Now remember, the tube itself, it's a property of the material. So for example, I have this piece of fiber optic plastic, and if I take a look at this particular thing, all right, I look, it has no coating on the outside, there's no mirrors or anything like that. So if I'm looking here, light goes in the one end and actually gets trapped inside it. So if I were to take, for example, my overhead projector and plug that in carefully, I would actually see that the light itself becomes trapped inside the tube. I hope the angle's good enough. Now remember, the light's coming out of the projector, it comes out of the end of the tube. Same thing with this one's used for medical purposes. If I take a look here, the light goes in the tube and then comes out the other end. Why? Because it's trapped. The light's exceeded the critical angle and now is forced to reflect. I can also take this same principle and use it with prisms. A prism is just basically a triangular piece of glass, and if I do this, I can actually take the light and shine it, and you can see that the prism becomes as a mirror, and you can actually get quite a bright image from the prism. Let me see if I can do a little better job of that. Let's see here. Bending, bending, bending. And you can see the prism itself is extremely efficient. Just a block of glass, no shininess or coating to it.